Yes. Yeah. The talk on conductor loop is the moment. Okay, it's the kind of moment. Uh the it's the force multiplied with the distance. So you can get the quantity which is called torque. Okay. In this. Yep. Let's consider the simplest case. Okay, that's uh, the simplest geometrical shape in uh, กสิดิกสิดิเหมือนว่าพิมพ์มาอันนี้ใช่ไหม the simplest geometrical shape you can find. Okay, it's the rectangle, but the theory here can be applied to any shape of the conductor. Okay, you can arrange the shape of the conductor uh, in any way. Okay, whether it's circle, it's oval or ellipse. Okay, or ellipsoid or something like that. It's also possible, but at the beginning step we're gonna consider only the rectangular shape. Okay, yeah, and we will see that in the example there is also the case when we have the conductor y in the forms of triangle or rectangle. Okay, or circle. Okay, any kind of shape that we can use. Okay. Okay. Yes.ส่วนลิงก์ที่ YouTube นะครับคุณไปเลือกเอาดูนะครับมันมี2อันนะครับ Okay, in order to not waste our time. Okay, we have here the conductor in rectangle form. Okay, let's say the rectangle has two things. All right. The mouse. The first one has two sides. Okay, two different sides. It can also be the square. Okay, typical square, and in that case you have the same distance to all four sides. All right, but rectangle has two different sides. Okay, it's called A and B. Okay, in this case width and length. Okay, in yeah, that's the simplest shape you can find it. The area and so on is quite simple to be found, right? Okay. Yeah, and you can have also another possibility to arrange your conductor. Well, let's say there is an input. Oh, sorry for that. There is a point where you can let the current flow in through this. I'm not sure I share the screen already or not. ยังไม่ได้แชร์ใช่ไหมโอ้ sorry มีคนขอเข้านะครับ มีแจ้งมาที่ไลน์เลยนะถ้าเกิดผมมัววุ่นแล้วไม่ได้มองเห็นคุณนะครับ I didn't share the screen right here. Okay. พูดอยู่ตั้งนานแต่ว่าไม่ได้แชร์หน้าจอครับ alright, it's already there, right? Okay, I hope that you can see the board the screen from this machine. Alright, yeah, here let's say we have the rectangular shape of the conductor loop. Okay, in you can let the current flow in this direction. All right, in Where else? And the arrow of the returning current is gonna be there, okay? But they don't represent this part, okay? For simplicity, they just write down the simple rectangle, okay? But there should be input and output so that the current can flow in this square or no rectangle conductor. Okay. Yes, when the current flow in this from this one, okay, from this point, and it's gonna return to this line or like right here. Okay, that's the top view. Okay, we look at this rectangle conductor from the top view. Okay, from the top aspect, and if we let the magnetic field, okay, take place, okay, or flow through this conductor, okay, from left to right, okay, with the green arrows here, you can see that there will be some effects. Of course, the most important quantity for us in physics is going to be the force, right? That's the most important thing. Yeah, force is the main interest in physics, right? In yeah, we will determine the force, but the sophisticated term or quantity apart from the torque is apart from the torque is the so-called torque. Okay, torque is, as I told you, torque is like a moment, is the multiplication of the force and the distance you wanna let it be the reference or rotating points. Okay, in with that referencing point, okay, you measure the distance from the rotating one, and oh no, the rotating point to the point where you see the force acting on that bar, on that object. All right, and that's the way we have the force or the torque, right? The torque is the extension, okay, the sophisticated one, okay, but it's not too difficult at all for us to understand. All right. Yeah, we go ahead with the next on the next page. This is the side view. Okay, it's the same thing, but we look at it from the different perspective. Okay, from the different angle. It's the side view. All right. In yeah, with this one you can see simply that there is force acting on the conductor, but I will tell you later how we could determine the direction of the force. Okay, and that's it, right? Okay, we need to determine the direction of the force. Okay, if we take a look at this, F1 is going to be point here. Okay, it's directed upward. Okay, it's directed out of the lecture notes in this on the model or on the screen, right? And the force F number 2 is going to have the cross sign here is pointing down, right? According to this notation, right? So how could we find? How could we determine, or how could we conclude that the force on the left side is pointing upward, and how could the force on the right side is pointing downward from this figure? Okay, you just follow the idea from the previous topic. It's F equal I and vector L cross vector B, right? That's what you have found before, right? And of course, when we have the once we have the current flowing in this direction, it means our vector L is gonna be here, right? In this direction, that's the vector L. And yeah, you have L, right? In this one, in the pointing in this direction, and you have, of course, the magnetic field here, vector B, like this. Okay, when you curl or turn or rotate your four fingers from L to B, right? From the first vector, the vector number 1, to the vector number 2. All right, you will find that your thumb direction is gonna point upwards here. Okay, pointing is gonna point out of this plane. Okay, that's why you get the dot symbol here, the force on the left side, which is denoted by the F with subscript number 1, okay, on the left side is pointing out of the plane, okay, or if you look at the side view is pointing upward. โอเคงงไหมครับไม่งงนะทางด้านซ้ายนะครับมันมาจากสิ่งที่คุณเรียนรู้มาก่อนนะครับ ILB นั่นแหละโอเคไหมจะ QVB ILB ใช้มากครับกดมือขวาห้ามลืมนะครับทั้งที่ผมบอกว่าเรียนมาเรื่อยๆห้ามคุณทำมือขวาหายครับใช้มือขวาอย่างงงนะครับโอเคถ้าหมุน3นิ้วไม่เป็นเอาหมุนเป็นง่ายๆสุด4นิ้วนะครับโอเคไหม4นิ้วจากเวกเตอร์ที่1 L ไป B นะครับแล้วคุณก็จะได้ผลลัพธ์มีอะไรเตือนมาหรือเปล่าis there anybody okay someone is gonna join okay hear the lecture anyone else no นะ what happened okay well yeah that's the first that can take place on the left side. What about the force direction on the right side? Of course, we have here the current flow flowing in this direction, right? And it's going to get out this way, right? It starts from here, right? Yeah. Yeah. But we neglect the small distance here. All right, we neglect the losing area here. Okay, losing coverage of the connector. Okay, we can simply look at this configuration as the perfect square rectangle. All right. Of course, we on the right side we have here vector L, right? It's vector L because we've borrow the direction of the current and we borrow the length of the L, right, on this side, which is B. Okay, the length of L on this side is B. All right, and the second vector is gonna be vector B, right? Magnetic field vector, and of course you have to apply again the FILB formula in order to find the output direction, which is the force here. Okay, let's start to rotate our four fingers. You can start from the first vector L to vector B like this, right? And you will find that when you use your four finger, right, the force is gonna point downward, okay, pointing into this lecture node, and that's why we get the cross sign, which represent the rear part or the tail of the arrow. Okay, and yeah, that's the force. Okay, on the right side we have the force pointing out of the plane. On the right side we have the force pointing into the plane. And if we take a look at the same figure but from the side view, you can see that you have the force on the right side pointing up and force on the right side pointing down. And this the reason why we have talked on this copper y. Okay, it's like the bar. Okay, you have the moment. Okay, this is the rotating point. Okay, or reference point. Rotating point. โอเคถ้ามีคำถามอะไรเขียนอยู่ในไฟล์เลยนะครับผมแชร์ให้คุณมากที่สุดนะครับโอเคไหมอาจารย์ครับมันต้องเป็นแบบนี้ครับผมคิดว่าอย่างนี้หรือผมมีคำถามคุณวาดรูปมาในสไลด์อะไรเลยนะครับไม่ต้องเกรงใจผมนะครับขัดจังหวะได้ทุกวินาทีนะครับโอเคไหมเอาที่คุณเข้าใจมากที่สุด alright yeah, this is the reference point or the rotating points in of course you have the let's say this is the center of the clocks and here is the clockwise direction, right? Clockwise okay, clockwise direction, and we are gonna have the talk on the clockwise direction, right? Because it's try to keep this conductor rotating. Okay, so it's the circular force. Okay, it's trying to rotate this one. Okay, let's say this is the reference point is fixed and the conductor loop is gonna turn or rotate according to this arrow. Okay, because if the force on the right side is pointing also upward like this, there will be no rotation. Okay, it's gonna move upward. Okay, but on the left side it's pointing up, on the right side it's pointing down, so it's gonna move this conductor in terms of rotation. All right, and yes, the moment on the left side is gonna be the torque, right? Torque is force time distance, right? The clockwise direction. Not sure. All right, the torque on the clockwise, because there is only clockwise direction. The first one is F1, right? The magnitude F1 times the distance, and what you may observe is that the distance here is, I don't know. Well, here is A, right? Here is the A, but our referencing point or reference point is gonna be here, half this side, right? Okay, the rotating point is half the width side, so the distance here is gonna be half of that. Okay, is A by 2. Okay, and another side is A by 2 as well, right? And that's why we have here the distance A by 2 as well from the reference rotating point, okay, or reference point. Okay, and the distance is A by 2, right? So you have F1 times A by 2. Okay, and this is one of the torque that can happen with reference to this point. Okay, it's the counterclockwise. Okay, try to rotate this bar in the clockwise direction, but there is another potential or the possibility. Okay, here on the right side you have F2. Okay, and is pointing downward, and the distance from the reference point is also A by 2, right? So you can write down here the torque is doesn't include only a single F1, but also F2. Okay, and the distance is gonna be A by 2, right? And if you go into the detail, you will find that F1 and F2 are the same. Okay, and F1 and F2 are the same, and let's say F1 and F2 be F, okay, without subscript, and you're gonna see that torque will be F A by 2 plus A and F A by 2, right? And it's gonna be A F, simply like that. All right, it's not too difficult, right? yeah, we will go into the detail later. What is actually the expression of the F, okay, which is the magnitude of the force for those two forces, okay, and here is the situation when the loop or the conductor can stay at any position. Okay, any position means that at any angle. Okay, and what is the angle? The angle that we will say in this topic is the angle between this is the plane, right? The plane of the circular conductor, the rectangle loop or the conductor Y, right? And of course, any plane is gonna have the so-called normal vector. Okay, ก็คือ vector ตั้งฉากกับระนาบนะครับ okay, normal vector of that plane. Okay, the conductor actually is not a plane. Okay, it's not a smooth surface, but it's made of the uh, the 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 loop of the conductor, but and we imagine that the surface that includes these include the area of the whole conductor is gonna be the plane. Okay, but there is no plane at all. It's only the conductor loop like this. Okay, but we assume that the air and space here, okay, be inside the conductor forms the plane, right? And any plane is gonna have the normal vector, and the typical property of the normal vector is that you have right angle, which is 90 degree from the plane, okay, the plane surface to that vector. And the angle we will talk about in this topic is the angle between the normal vector of the plane. Okay, it's not the angle of the plane itself with respect to the magnetic field. Okay, it's the normal vector of that plane with respect to or measure comparing to the magnetic field like this. All right, yeah, this is the instant that we can have, right? Because when the conductor starts to rotate, it can have any angle with respect to the magnetic field, and we're gonna see what is the torque at that moment and what is the force at that moment actually. Okay, and this is the result we have taken from the book, and they just say BIA sine theta. We will go into the detail later why we get the BIA sine theta. What is B? B is the magnitude of the magnetic field vector. All right, that's what you get familiar or get used to it, right? It's the magnitude. It's in Tesla, right? The unit for the magnetic field or magnetic flux density is Tesla. And what else? The next thing is I, right? Oh, this is quite simple. Okay, this the most understandable quantity. It's the current, and the unit of the current, of course, is the unit of the current is ampere, right? Yeah, I, okay, is the current flowing in that conductor. Okay, current. There is nothing more. Okay, forget about the I for the light intensity in the first chapter. Okay, we don't use it anymore. I will be considered only as the current at the moment or even in the next few chapters. Okay, the next variable is A, right? A is the area. Okay, area, for example, you have the rectangle, all right, like this. All right, and this side is A. This is the width, and here is the length. Okay, all right, the area of this rectangle, of course, this is what you may have seen in your primary school. A rectangle is equal to width times length, right? It's gonna be A times B in this rectangle setup, okay? If you want to get fantasy apart from or different from the rectangle shape of the conductor or the copper wire, you can also prepare your conductor or copper wire in circular shape, okay, in ellipse shape, in oval shape, or the heart shape as well, okay. You can have also the conductor in this in this shape, okay. It's up to you, okay. But the important thing is that the area, okay, of this conductor, that's the most important thing, okay. Area of hearts. But I don't know how could we find analytically, but you need to be able to get the function of the heart curve here, and then you make the integration, you can get the area, okay. You can design or use any shape of the conductor, up to you, okay, as you like. But the simplest case for you at the high school, we're gonna consider the rectangle first. All right, there will be triangle shape later. All right, that's the first glimpse or the first glance or at the talk, right, that happened in this setup. And here we can determine the torque by or in terms of the moment at the pivot, okay. Pivot is the rotating point or the reference point, as I told you, okay. Pivot is the rotating point. And what else? The in Newton meter, okay, that's the standard unit in physics, okay. Apart from spatial unit like ampere, Tesla, Weber, okay, that's the spatial kind of unit in physics, right? In this quantity, the torque, that we don't have any special name for the unit, okay. I don't know, maybe no, there is no proof that who is the first person who discovered the torque in physics, okay. That's why they don't give the surname of any person to this to the unit of this quantity. Okay, all right, at the angle theta, like this, okay. Please open your mind, okay. Sometimes we will use phi, okay, to represent the angle between the normal vector and the magnetic field direction, okay. In some books they use the Greek letter phi instead of the theta, okay. Please be open to that, okay. Don't get strict to only the variable theta. It can be also phi, okay. But generally speaking, it's the angle, okay, between the normal vector and the magnetic field. All right, A by 2 is, this is what I have already provided here, right? But this one is the situation when here is the normal vector, right? Normal vector of the plane, right? Normal vector, and the angle between the normal vector and the magnetic field. Here is the magnetic field, right? The angle between normal vector and vector B is the right angle, okay. And that's why we don't have nothing at all at this location, okay. You can see this is the number 1, right? Number 1. And yeah, actually it's sine theta, all right, but theta is 90, that's why we get only number 1 here, okay. The general version is this one, okay. F times A by 2 sine theta. Why we say A by 2 or 1 by 2 sine theta? Because this is the lifting force, right? This is the lifting force right here, right? This one is the lifting force, okay. and ใช้ยางลบก็ได้เหมือนกันบางทีผมขี้เกียจขยับเมาส์ผมก็จะใช้ปากกาขูดตรงนะครับแสดงยางลบนะหมายถึงตำแหน่งนะครับว่าที่ผมกำลังพูดถึงอยู่ตรงไหนครับบางทีมันขี้เกียจเลื่อนมือไปจับเมาส์นะครับโอเค เพื่อความรวดเร็วของเราครับโอเคthis is the lifting force and here is the pushing force okay pushing downwards and again we have to consider the torque at this moment okay when the angle is theta and it's gonna be the force right F1 or simply F okay F1 times the distance is over there here okay from this one from this point to this one because right now we have the length of the bar okay in order to compute the moment like this all right here is the pivot or the rotating position all right เมาส์จะดีที่สุดนะครับ reference point and here is the place we observe okay we we can imagine that the force is acting actually at this location okay F1 is here okay and the distance okay is measured from the place where the force exerted on to the rotating point okay it's not a by 2 anymore okay a by 2 is here okay the length of the conductor is over there already but the distance here is not a by 2 but I don't know there is okay there is a factor okay inserted at the end of a by 2 and of course when we write down the triangle okay we would see that okay here is the angle phi right but the angle between the normal and the plane should be 90 right so the angle here this one okay this one should be should be 90 minus okay 90 reduced by theta right this angle is gonna be 90 degree minus theta it means that this is the right angle right it means that this is the angle theta right and of course the distance here could be as we know this is a by 2 right this is a by 2 and this one will be what is that this is theta this is a by 2 times psi all right and that's the reason why we have the distance here okay distance here a by 2 times psi theta all right okay from the with respect to the rotating or the pivot or the rotating points okay and that's why we get the distance which is shorter actually okay because if you look along this direction you look at that along this direction you find that the length here is a by 2 but in this configuration when it's tilted by theta the distance for the force that acting on the bar or the rotating object is a by 2 times psi theta only okay it's shorter than a by 2 and you can see that the torque is reduced okay the torque decreases by the factor psi theta and f1 f2 will be the summation okay because a is the same psi theta is the same okay the object made by copper doesn't have the bending shape okay it's rigid object so theta is the same okay and the symmetry between both sides on the rotating point will give you a by 2 for both moment calculation and that's why we get the same thing okay when we have the same thing we move it and we get only f1 f2 added to each other like this and if we get into the detail from what we have learned before right it's ILB sine theta, right? The magnitude, you can see here that ILB, because F is ILB, right? From this expression. And what is vector L? Vector L is the vector that follows the direction of the current, right? Direction has the direction has the same direction as the direction given by the current, right? The current I. All right. And vector L has the magnitude magnitude by here this portion, okay, which is B. All right. And so as the magnitude of B, okay, according to this configuration. And yeah, L has two things, right? The direction and the magnitude. Direction as the current, magnitude according to this one, okay, it's only B. Okay, we doesn't count the length here, okay, because it's not the distance that can bring us or give us the force. Okay, there is no induced force in this one. Okay, and also what happened? Hello. What happened? My God. All right, maybe I get stuck with that. Oh, I don't understand. Maybe there is an internet problem. All right. เดี๋ยวครับขอเสียบหูไว้สักข้างนึงครับโอเค alright กลับมาแล้วนะครับไม่มีใครแจ้งผมนะว่ามันหลุดครับ14 I think it's 13:50, right? I need to leave you because you should have the break of 20 minutes, right? Okay, let's get to the our rationals again, and I have given all the detail to you. FILB, right? It's I, right? And L, okay? L is the length, B is the. What is the reason why we get B? Because the length of the vector L is B, okay? And that's why we get B, okay? I small b and capital B. Of course, you know that the capital B means the magnitude of the magnetic field, right? So it's quite simple. In order to get better quality, we are going to use only the mobile data, right? นะครับเพื่อไม่ให้หลุดนะครับใช้ซิมอย่างเดียวนะครับ 5G นะครับ alright, and yeah, when you put all the stuff here, IBB, right? IBB into this expression, okay? Because F1 and F2 are equal in magnitude, as I told you, okay? But they are both are different in direction. They have opposite directions to each other, but they have the same. Both have the same magnitude, and we can substitute it into this one, okay? Equation 47. And what you're gonna get, as I told you, there will be factor 2, right? When two things are added to each other, you will have number 2 in front of that term, and these two will cancel 1 by 2, okay? That's the half of the moment side, okay, of that conductor. 2 and 2 will cancel each other, and you can see that AB, okay, the term AB. And you can see that in rectangle, right? Like this, you have A and B here, right? And of course, A times B is what you may have heard before in your primary school, is the area, okay? Area of rectangle, okay? And that's quite simple, okay? It's not difficult to understand, okay? AB is the area of the rectangle, and that's why we are gonna replace it, okay, by the capital A, which is the area of your conductor, okay? And we don't go into the detail, the length sides, the width sides of the rectangle anymore, okay? We won't talk about it. We will simply say or consider the area of that conductor only. All right. And yeah, you can see that the expression become A I B sin theta อันนี้สำคัญครับพบได้เรื่องนี้ยาวๆครับโอเคไหมA I B or you can say is B I A sin theta. It's up to you, okay? The way you will remember, you can say I prefer this word E bar, okay? I B A sin theta. It's up to you, okay? Okay, you may prefer A I B B I A I B A